Hello, I'm Hiroyuki Miyoshi. I'd like to talk about analytical solutions of drawing flow through microfluidic channels. This presentation is based on a paper published in Journal of Engineering Mathematics last month. Superhydrophobic surfaces can dramatically reduce the flow resistance in the manipulation of fluid in microchannel devices. The left figure shows a typical superhydrophobic channel flow. Because of the surface tension of water, the interface or menisci can span the gap between the grooves. But as shown in the right movie, the deepening of the menisci from the top of the grating occurs due to the pressure fluctuations of gas or mass transfer. And it is known that the deepening is bad for slip. So we are going to quantify the effect of the deepening. These are several numerical techniques for obtaining superhydrophobic channel flow. N and 1 use the Fourier series expansion to calculate the semi-infinite channel flow in this geometry. Spragali and Prosperetti also use the Fourier expansion for the flow, and they found the curvature effect on the periodic free shear pattern. Moreover, they found the asymptotic expansion of slip lengths with respect to the protrusion angles. Teo and Ku use the finite element method for the computation of slip lengths. These techniques need numerical calculations. So we are going to find analytical solutions of specific superhydrophobic channel problem. This slide shows a summary of the previous studies of analytical solutions. Philip is the first to calculate the semi-infinite channel superhydrophobic channel flow and bounded periodic channel flow, where flat interfaces are flush with interspersed flat no-slip surfaces. By using a suitable conformal map, he finds analytical solutions of these two geometries. Claudia also used a conformal map to find the semi-infinite channel flow with partially embedded groups. In summary, these three geometries have an explicit solution for the flow WF, and then the slip lengths of these geometries can be calculated. It is important to mention that the normal superhydrophobic channel flow, the slip length is written by log sec term, and the semi-infinite channel with partially embedded grooves case, the slip length is written by log cosec term, and for the bounded channel flow, the slip length is written by in this formula. This is complicated, but by evaluating the Jacobi canoidal function, we can calculate the slip length of lambda. The natural question is, do we have an analytical solution for the bounded channel with partially embedded grooves? And the next question is, why is log sec formula I explained in the normal slip length? Why this formula is useful? This is because log sec formula gives a good approximation for the bounded channel. This graph shows a comparison of the semi-infinite channel and the bounded channel of the slip length. The pink line shows a slip length of G over L equal 1.2, and the cross dot corresponds to the semi-infinite channel case. As you can see, the pink line rarely matches to the semi-infinite channel case. The natural question is, for the embedded grooves, is log cosec formula useful for giving a good approximation? The answer is not always. I will show that these are key messages of the talk. In this talk, we explain analytical solution for the longitudinal flow with partially embedded grooves is derived by conformal mapping approach. And slip lengths for the channel with embedded grooves cannot be approximated to the same accuracy by the semi-infinite channel when the height of the invasion depth is large. Now, I would like to talk about a physical model of superhydrophobic channel with embedded grooves. Because of the periodicity, it is enough to consider the flow in this period window. We assume that the menisci are flat and the steady flow in z direction is driven by constant pressure gradient S. And following the previous studies, we assume that no slip condition on the wall and no shear condition on the menisci. Because of these assumptions, WF satisfies the Poisson equation with two boundary conditions on the wall and on the menisci. Because of the periodicity, dWF over dx equals 0 between the gaps. I will use this boundary condition in the last slide, so please remember this boundary condition. Now I'm going to talk about how to solve the flow by using the conformal mapping approach. We propose to use a conformal map from the triply connected domain to the period window. The conformal map can be written down in the explicit equation. Here, omega is called Schottky-Klein prime function, which is a special function calculated by using the GitHub code. The special property of the prime function is explained in this book in detail. Because we know the map, the solution for the flow can be written down explicitly. And this graph shows a velocity count approach. We change the gap of channels and we change the invasion depth. When we change the gap of channel, the flow pattern dramatically changes. However, even if we change the invasion depth, flow pattern does not quite change. All these graphs can be reproduced by using the GitHub code. Now we are going to quantify the slip length of the channel. Because we know the solution for the velocity, we can evaluate the slip length of the channel. In order to calculate the slip length, we compare the total flux of the channel with partially embedded grooves and the channel which has Navier slip condition on the boundary. By equating total flux Q and Q lambda, we can calculate the slip length of the channel with embedded grooves, and this is the explicit formula for the slip length of the channel. And this is a graph of the slip length of the channel with respect to h over L. H is the invasion depth. As you can see, the slip length decreases as the invasion depth h increases. This is because the more no-slip rays protrude into the flow, the more they will provide increased resistance. And another finding is the slip length matches the result obtained by the semi-infinite channel when G tends to infinity. So pink line shows the slip length of G over L equal 8.5, and the cross dot corresponds to the infinite case, semi-infinite case. So pink line nearly matches to the semi-infinite channel case. And I will check it carefully in this slide. This slide shows a comparison of the slip lengths of semi-infinite channel and the bounded channel. Red line is the slip length of G over L equal 2.5, and the pink line corresponds to the G over L equal 8.5. As you can see in this graph, the slip length of G over L equal 2.5 has a big gap, big difference from the slip length of semi-infinite channel case. This means the slip length for the channel flow with embedded grooves cannot be approximated to the same accuracy by the semi-infinite channel. The final remark is a connection with another super hydrophobic problem. We solve the flow with partially embedded grooves, but by rotating 90 degrees, our method solves the periodic channel flow with super hydrophobic surfaces. So our method can solve both normal super hydrophobic channel flow and super hydrophobic channel flow with partially embedded grooves. This means the flow obtained in our formulation generalizes the super hydrophobic channel flow. And this is a summary of the talk. Thank you very much for listening.